Okay, so think about this for a second. A simple jar of tomato sauce, right? Sitting in your pantry. You just expect it to be, well, good, perfect even. But did you know that getting it just right, especially the amount of preservatives in there, can actually involve some pretty advanced math? Welcome to the deep dive. Today, our mission really is to unpack some sources that explore this pretty fascinating application. How mathematical formulas, specifically using derivatives, can like optimize preservative levels in sauces made from agro-harvested tomatoes.
That's exactly it. Yeah, we're diving into these excerpts you shared, and they detail this specific intersection, food science and calculus. And the goal here, it's not just to say, oh, math is useful, right? It's to really get a handle on how concepts like differentiation are actually applied in a very precise, practical way based on this material.
Okay, so the sources aren't just hand-wavy like use some math, they actually dig into how it works for something like tomato sauce.
Exactly, no hand
Yeah.
waving. The sources describe a very real challenge manufacturers face. They need enough preservative for safety, for shelf life,
Mm-hmm.
to stop spoil it from microbes and stuff. But there are downsides if they add too much. You get potential changes in flavor, texture, and obviously it costs more.
Ah, okay. The classic optimization puzzle. Finding that sweet spot, the just right amount.
Precisely. And the sources really emphasize that just, well, guessing or using rough estimates, it's just not precise enough. Not when you need to balance these things optimally. So they point towards using mathematical modeling.
Okay, modeling. So where do derivatives fit into that picture, according to these sources?
Well, the sources explain how they build a mathematical function first. This function tries to model the outcome they care about. Could be predicted shelf life, maybe, or even a combined score for quality and cost.
Yeah.
And it's based on the input variable, the preservative concentrate, let's just call it C. So they're looking for the value of C that gives the absolute best outcome from their function, you see.
And derivatives. They help find that best outcome, that optimal C.
That's the key. That's where differentiation comes in. By taking the derivative of that function,
Yeah.
specifically with respect to C, the preservative concentration, you're essentially calculating the rate of change. How fast does shelf life or that quality score change as you tweak C? And you look for where that rate of change is zero,
Rate of change is zero, which means
which basically means you've found the peaks or the valleys of that function, the maximum or minimum points. And the sources indicate they use this math to find the specific level C that, say, maximizes shelf life within cost limits. Or maybe it minimizes cost while still guaranteeing a certain safety level. It depends on how they define their goal in the model.
that makes a lot of sense. So instead of just endless trial and error in the lab, they use the math to pinpoint exactly where that sweet spot, that optimal concentration, lies. Based on how all these factors interact, did the sources say why focusing on agro-harvested tomatoes specifically was important for this?
Yeah, that's an interesting detail the sources brought up. They didn't go super deep into the why, but they implied that the specific characteristics you get from large-scale agro-harvesting, maybe more variability in ripeness, or enzyme levels, initial bacteria counts, compared to other methods, maybe.
Yeah.
Anyway, these factors introduce specific variables, perhaps some noise, into how spoilage happens. And that makes this kind of precise mathematical optimization really valuable for keeping quality and safety consistent across huge batches.
Huh. Fascinating. So it's not just a generic math exercise, it's actually tailored to the nuances of where the ingredients come from. Did the sources mention anything about the results, like the benefits they actually see from using this approach?
They suggest it leads to a more consistent product, definitely more reliable than just empirical, like trial and error methods. By calculating that optimal level so precisely, manufacturers can potentially cut down on unnecessary preservatives, which, lowers costs, might even improve taste, all while still rigorously ensuring the shelf life and safety standards they need. It's all based on the source data.
Wow, okay. So next time you grab that jar of sauce, you might actually be holding a product that's been like silently optimized by calculus, making sure it's safe, tastes good, and was made efficiently. That's kind of cool.
It really is. It adds a whole new layer of appreciation for the hidden complexity in just everyday things, doesn't it?
Absolutely. So we just took a deep dive into how applying derivatives, as laid out in the sources you shared, can optimize something so specific, preservatives in tomato sauce. It's a really clear example, I think, of these complex math concepts delivering real tangible benefits in places you wouldn't expect.
For sure. And maybe it leaves you with this thought to chew on. If optimization, using derivatives to find those peaks,
Yeah.
Ideal balance, if that's quietly working away in your pantry, making your sauce just right. Where else? Where else in the world around you might this kind of detailed mathematical thinking be optimizing things, making them better or more efficient without you even noticing? Might be worth keeping an eye out for those hidden equations.